Hello. Good morning. Happy Friday. Sorry that I had to start a little late today. Hopefully that didn't mess up your schedule. You can see the periodic table behind me. Today we're going to be looking at ions and ionic compounds. And for that, we're going to fill in a lot of the parts of the periodic table that we haven't really talked about much. So in the previous module, we really focused up here on carbon. I can't get my pen that high, but on carbon, nitrogen, oxygen, hydrogen, organic chemistry. And now we're going to talk a little bit about the compounds and some of the compounds in the rest of the periodic table. So it's not that these compounds can't do the same type of bonding that carbon does. It's more that it's just less predictable. And if you go on and study more chemistry, you'll learn more about kind of the idiosyncrasies of the individual elements and the things they can and can't do. But for today, we're going to focus on ions and ionic compounds. So if I pull this out here, what we've talked about up to this point have been called covalent compounds. That is, the atoms are connected by shared electrons in those bonds that we draw the straight lines to represent. And those are the structures that we've been talking about. And so the types of structures we're going to talk about today, we're not going to draw with those same kinds of lines. We're not going to draw Lewis structures, line structures. It's a different way of atoms to organize themselves and to connect. All right, so first, let's just review from a couple units ago when we talked about ions. So remember from that unit on atomic structure that ions are charged atoms, which means that the number of protons in the nucleus, the positively charged protons, is not the same as the number of electrons going around the outside of the atom. So in a charged ion, you have an imbalance there, and you can have two different types of imbalances. You can have what's called a cation, which means that you have a positive charge overall, and therefore you have more protons than electrons. You can also have an anion, which is a negative charge overall. And in that case, you'd have more electrons than protons. All right, so those are the two types of ions, cations and anions. And so let's take a look at how we deal with those and what those mean. All right, so for example, let's look at sodium. Now, the chemical symbol for sodium is Na. And so if we're talking about sodium and we just write Na, like that's our reagent, that's our whatever that we're talking about, what we're really saying there is that we're talking about a neutral atom of sodium. So if we look at the periodic table, we find sodium. It is over there to the left. You can see it's atom number 11, the third from the top on the far left column there. And because it's atom number 11, if we review, we know that means it has 11 protons and 11 electrons if it's neutral. Remember, we can't tell the number of neutrons from the periodic table. So 11 protons, 11 electrons. So going back here, let's just write that down to review, 11 protons and 11 electrons. All right. So now, if sodium were to lose an electron, it would become the sodium cation, which is still called sodium. It would still have 11 protons because that's the atomic number, and that is what makes sodium sodium. But now it would have 10 electrons. And to express that, we write that with a plus sign. And as you did in that unit before, you can have +1, +2, +3, whatever. And since we want to balance this, we want to say that there's an electron that's gone. So that's how we express that. An E with a little minus sign is an electron. So in this process, we have sodium with 11 protons and 11 electrons, regular neutral sodium. Then it loses that electron, and There it is. So it just kind of disappeared. Now, these species are totally different things. Sodium is a highly reactive metal. You can look up a video of somebody throwing sodium into a lake, and you can see that it just like explodes because it's so reactive with water. So pretty unstable. It's also really kind of a weird metal in that it's soft. You can kind of cut it with a butter knife. And when it loses that electron, it becomes a sodium ion, which is totally stable and is something that's in our bodies, that's important to our function. That's what's in sodium chloride salt. In seawater, that's the sodium in seawater. So the sodium, that kind of sodium that we experience is almost always the cation, the sodium cation, not neutral sodium, the sodium metal. So that's an example of a particle becoming a cation, sorry. All right, so to look at the other side of this, let's look at chlorine. Its chemical symbol is Cl. And chlorine in its atomic state actually exists as a molecule, as Cl2, so 2 chlorine atoms connected together. And it's a gas, and it's a poisonous gas. But when it, sorry, didn't do this right. When it gains electrons, it's actually going to have to gain 2 electrons to make 2 ions. Now, here's our chloride ion. So Cl, again, if we look at our periodic table, chlorine's right up here, and it's number 17, so 17 protons, 17 electrons. If we add an electron to each atom, remember we're dealing with 2 atoms here, so we add 1 electron to each, then we have 18 electrons and 17 protons. So that's an overall negative charge here. And so that's what we call an anion. Now, anions actually change their name from the original atom. So this is called chlorine in its elemental neutral state, and the ion is now called chloride. So we add that "ide" suffix when we make anions, but we don't do that to cations. Cations just stay sodium. So sodium, sodium, chlorine, chloride. Chlorine becomes chloride. All right, so this is forming the individual ions. So now when we talk about ionic compounds, what we're saying is that in nature, ions don't exist like by themselves. You can't get a jar of sodium ions or a jar of chloride ions. Ions always have to have their charges balanced out. And so when we see a compound like sodium chloride, what we have there is a combination of the 2 ions that we just talked about. So we have sodium ion, Na+, and we have chloride ion, Cl-. All right, good so far. So that's what we're talking about here. And then when these combine, they combine always in a ratio so that the overall charge is neutral. Now, there's some exceptions to that, but for this class, we can use that as a rule. So we'll just say that an ionic compound is ions combined together for or to make an overall neutral charge. So the way we calculate that and the way we set that up is we look at the 2 ions and we look at the cation, the anion charges, and we know we have to ultimately in the compound have as many pluses as we do minuses. They have to balance. So for this one, it's pretty easy. We've got 1 plus and 1 minus. So if we just have one of each of those, we have a balanced compound. So the formula for sodium chloride is NaCl. And that's it. And you've probably seen that before, NaCl. And that's where it comes from. But using this idea, if we can figure out the charges of the different ions, we can always put together the correct formula. So if you hear a name like sodium chloride or barium chloride or potassium oxide or whatever it is, if we know the charges of those ions, then we can put those together and make an ionic compound and write the correct formula for that ionic compound. So before we can do that kind of for anything, we need to know how we can find the ion charges. So the answer to this is, well, we can't always. We can sometimes, and other times we can't. So we're going to focus on the times that we can. And the way that we can, let's draw a periodic table here. All right, I think that looks pretty good. Let's check. Yep, all right, that'll work. So it turns out that certain areas of the periodic table have predictable ion charges. Elements in those areas always have the same charges. And if we just remember a couple of those areas, then we'll always know. And as an online class, you can always look this up too. So let's mark those areas here. So the first one is the first column. Second one is the second column. All the atoms in the first column are going to make +1 cations. And all the atoms in the second column are going to make +2 cations. So if we go back to looking at our periodic table here, that's hydrogen, lithium, sodium, potassium, rubidium, cesium in the first column. And then I'm skipping a couple because I know there are some exceptions, but basically magnesium, calcium, strontium, barium in the second column. So if you just remember those columns and it's column 1 is +1, column 2 is +2, then any ionic compound with those atoms is going to be made of that type of an ion. All right, let's look at the other side now. So we've got the far right column we can actually ignore because we don't make ions. Those atoms don't make ions. So that would be over in column 8, the noble gases. Actually, we'll say it's 18. Then we've got 17 and 16. And, I'm going to run out of space here. Okay, we'll make some skinny columns. I should have drawn this a little bigger. That's okay. So column 15, going from the right then, column 18 we're going to skip, doesn't make ions. Column 17 is generally going to be -1. And then we can kind of count back from there. So -2, -3. We don't generally have predictable ions in the fourth column. And then in the third, there's really just one, which is aluminum. And that's always going to be +3. All right, so it is a few things to remember. Going from the left, you've got +1 ions, +2 ions. Going from the right, you've got nothing, and then -1, -2, -3. And then you got to remember aluminum over here is +3. So looking back at the periodic table, all right, so we've got our -1s, -2s, -3s, and then aluminum +3. And then way over on the left are the +1s and +2s. All right, so let's use that information now to build some other formulas for ionic compounds. Let's start with calcium fluoride. So how do we come up with a chemical formula for the correct chemical formula for calcium fluoride? Well, first step is just to get the atoms and get the symbols. So we look at the periodic table, we look up calcium and fluoride. Remember that anions get renamed. So we're not looking for fluoride, we're looking for fluorine. And it's right up here, number 9. And then calcium's over on the left here, number 20. So we can write those down. Ca and F. So that's our first step, just getting the symbols. Remember, you don't have to memorize these. You always have access to a periodic table. You can print one out. You can pull one up on the internet, whatever. If we were on campus, you'd have them on the desks or whatever in your lab notebooks. Okay, so we've got these. So the second step then is let's find the charges. So we're going to use this table to locate calcium and fluorine. It turns out that calcium is in that second column and fluorine is over here in number 17. So that means that those are in the areas that have these predictable charges. So we can say that we expect a calcium ion is going to be +2 and a fluoride ion is going to be -1. Right? So we've got our charges. We've got our ions. So then the final step is to put them together in a ratio that makes the charges cancel out or balance or however you want to think about that. We need a 0 overall charge, which means this can't just be calcium. It can't just be CAF because that would be one of each, and then we'd have more positive than negative. So the way to deal with that is we need more negative. So we add another fluorine. Now we've got +2 and -2. That balances, so that works. And the way that we express that in a formula is with a subscript. So CaF2. All right, so that type of a formula looks very similar to what we saw with the covalent compounds with carbon. But in those compounds, we were actually counting the exact number of atoms that were in a molecule. In ionic compounds, they're these kind of big cage-like structures with a whole bunch of ions in there. So all we're expressing in this case is a ratio. We've got 2 fluorides for every 1 calcium, and the charges have to balance out. All right, let's try another one. Let's try aluminum oxide. All right, aluminum oxide. So we're going to do the same thing. We're going to look up aluminum, which is also sometimes known as aluminium. That's a reasonable, just an alternative of pronunciation depending on where you are in the world. The symbol for aluminum is Al, and the symbol for oxygen is O. So that one changed its name a little bit from oxygen to oxide. As you get used to this and do some practice, you'll see, you'll start to get used to some of those changes. We've got aluminum, we've got oxygen or oxide, and we're going to look up those charges again. So we find aluminum, which is right up there. We find oxygen, which is up here, and that's in those locations that we know. So we know that aluminum is going to be +3, and oxygen is going to be -2. All right, those are the charges on the ions. So now we need to balance the ratio so that we have an overall neutral charge. To do that, we have to use integer values. So we can't use a piece of an ion. We have to use whole ions. So one nice way to do that, at least until you get used to it, is just to draw them like I did here, just kind of adding a second one or a third one or a fourth one, however many you need, until you get them to balance out. So we'll say, okay, we've got 3+ on aluminum, 2- on oxygen. So we're going to add another oxygen. But that doesn't really solve the problem because now we have 3+ and 4-. So that's not the answer yet. But we can adjust these ratios however we want until we get it right. So one thing we can do is just kind of go back and forth adding ions until we get them to balance. So let's add a second aluminum. Now we've got 6+ and 4- overall, and another oxygen. And look at that. Now we've got 6+ and 6-. Now, if you knew some things about some math, you could probably have figured out that that was the ratio you needed to do. But you can just as easily figure it out this way. So you can see here, overall, if we have 2 aluminums, we have six positive charges, we can say. And then overall, if we have 3 2-, we have 6-. So that balances out. So the way we want to write this formula then is Al2O3 to show that we need to put these together in the ratio of 2 aluminums to 3 oxygens. Okay, hopefully that makes sense so far. So you'll notice in these examples, we're always going one direction. We're starting with a name and we're writing a formula. It's a lot harder to go the other way. You need to know all these rules about how things are supposed to be named. So we're not going to do that in this class. If you take another chemistry class like 121, you might learn those things. But for this class, we just want to be able to write the formulas so that we know what types of compounds we're working with. All right. We're going to keep practicing this, but we're going to add little wrinkles in here as we go. So the next wrinkle is, what about the rest of them? What about all those other elements that we see in here that didn't fit nicely into those +1, -1, -2 columns? And the reason those don't fit nicely in those columns is because those atoms, specifically these ones kind of all in the middle area, can have multiple different charges. So they can be +1, +2, +3. The good news is they're almost always cations. So all the metals we talked about last module, the metals versus nonmetals. That's fine, but we don't know the charges. Sorry, I got distracted by something there. We don't know the charges, so it's not quite going to work the same way. So what happens is, in those compounds, we need a little bit more information. So in the names of those compounds, the charge on the cation is actually given. So if we take, for instance, iron, if we look at a compound of iron, we might see something like this: iron 2 chloride. So we have this Roman numeral 2 in parentheses as part of the name. And that's because there are multiple different iron chlorides. There's iron 2 chloride and there's iron 3 chloride. So we have to specify which one we're talking about. And the way we do this is with this Roman numeral. And that indicates the charge on iron. And this is a really important point that is commonly, that I see commonly missed or mistaken. Everybody wants that number to mean the subscript, to mean, oh, it's iron 2, so then we're going to go Fe2. But that's not right. It's not the subscript. It's the charge. So you still have to go through the process that we just went through with these other examples above, but you're just told the charge instead of having to look it up on the table. So the rest of the steps in the process of finding this formula are the same. We need to write down our symbols, and we need to put in our charges. Chloride is -1, that we get from the periodic table. But iron's charge we get from that number. So we're going to write 2+ there. That's the charge on iron. And now we put the compound together just as we did before. So we've got +2 and -1, which means we need another one of these. So that means the overall charge, or the overall formula, has to be FeCl2. Notice there's no 2 here. Right? It's a 1-to-2 ratio between iron and chloride. The 2 here indicates the charge, not the subscript, not the number. Right? So that's how it works for all of those middle compounds, that their charges are not predictable, and so we need to instead actually specify the charge in the name. Let's try another one of those. So if we look at the periodic table, there's a pretty big range, including the ones that are kind of behind me here, that do that, where they have multiple different possible charges, and so that has to be specified in the name. So let's try another one. Let's try copper 1 oxide. So for copper 1 oxide, we're going to look up copper and oxygen on the periodic table. We've already dealt with oxygen, so we know that one. It's O, and it's always got that -2 charge for oxide. And then copper we can look up is Cu, and we now have a charge again. So Cu +1. Remember that number gives us our charge. So now when we put the formula together, we need 2 coppers for every 1 oxygen. And so our formula is Cu2O. So then let's compare that to copper 2 oxide. We'll just put that right next to it. Or maybe it makes more sense to put it underneath so we can see it better. Copper 2 oxide would be, in this case, the Cu would be Cu plus 2. The oxide is O minus 2. So now we do have a 1-to-1 ratio there because we can have plus 2 and minus 2. So our overall formula is going to be CuO. All right, so look at the difference of those 2 compounds and then the names. If you use that 1 for anything other than the charge, you're probably going to get the wrong compound, right? Like this one has a 2 in it, but there's no 2 subscripts because the 2 refers to the charge. So you use the Roman numerals to get your charge, and then you put the compound together just as before, making sure that everything balances out, that there's no extra plus or minus. Okay. The last thing that we're going to look at with regard to ionic compounds is what we call polyatomic ions. So some ions are not just one atom. All the ones that we've seen so far up here are all one atom. We put them together, and so the compound has like 2 atoms in it, right? Like copper and oxygen. Well, there's a class of ions that are actually made of multiple atoms bonded together. And these are called the polyatomic ions. And they are things that you may have heard of or may have used in some of your at-home experiments. We'll make a little table of some of the most common ones here. Again, you don't need to memorize these. You can look these up, use them on the table, but you do have to recognize when they come up in these names. So we'll talk about that. So we've got hydroxide, for example. Hydroxide is not the ion of hydrogen. It is OH minus 1. Nitrate is another common one, which is NO3 minus 1. So it's that whole thing. It's made of nitrogen and oxygen, but it's like all together in one unit called nitrate with a minus 1 charge. So you can treat it just like all the other ions, but you have to recognize that it's going to have a little bit different formula because it's this grouping of ions or grouping of atoms together in one ion. Sulfate is SO4 2 minus, another common one. We've got, there's a whole bunch of these. I'm not going to list all of them, just some of the more common ones here. Cyanide is CN minus 1. Phosphate is PO4 with a minus 3. And let's see, what else can we'll put in a couple more here. Carbonate. CO3 minus 2. And we'll add one. There's one common positively charged one, cation as well, called ammonium, which is NH4 plus 1. So these are some polyatomic ions. And the trick here is when you see a name and you want to write a formula, you have to recognize when the ion is not from the periodic table, but rather from this kind of a list instead. All right, so for example, let's say we have copper 2 sulfate. All right, and we want to write the formula of that. So we start with the same procedure that we've been using. We're going to find the symbols. We know copper is Cu, and we know now from this 2 that it's going to be plus 2. And then the tricky part comes here is with sulfate. So what is sulfate? If you just saw that word, how would you know if it was something from the list or if it was on the periodic table? Well, the way you know is all the ones from the periodic table, and you can go up to check this, all end in ide, I-D-E. And there's only a couple polyatomic ions that end in ide, hydroxide and cyanide. So if it ends in something else like ate or ite, then it doesn't come from the periodic table. It comes from this polyatomic ion chart instead. So when you're doing this for this class, another thing you can do is just always have a chart of these around so that when the ion names come up, you can quickly reference that chart and go, oh, okay, sulfate's on this chart, so I'm going to use SO4 2-. So when you find it on the chart, you have to take that whole thing together and put it here. And that becomes your ion that you're now trying to balance for the formula. So Cu 2 plus, SO4 2-, that's a 1-to-1 balance because we've got +2 and -2. So our formula is going to be CuSO4. And that's it. That's the formula. Let's do another one where we may have to balance it a little bit more. Let's look at how about barium phosphate. All right, so for barium phosphate, we're going to do the same thing. We're going to first write our symbols. So we get barium Ba from the periodic table. And then phosphate is in the list. So it's not phosphorus, it's not P, that would be phosphide, it's phosphate. So we look at the list and we write down PO4 3-. We also need to get that charge on barium. So we're going to find barium in the periodic table. It turns out it's right over there on the left near the bottom. So that means it's going to be in the second column, so it's +2. All right, so now we have one of those situations again where we have a +2 and a -3, kind of like where we had the +3 and the -2 before. So we're going to have to adjust the ratios of both, or adjust the amounts of both of them to get something that's overall balanced. So it turns out it's going to always be predictable in that way. So we're going to have 3 bariums and 2 phosphates, since each phosphate is -3. Now we have a total of 6+ and 6-. And the way we draw that, or the way we write that, is Ba3 for the 3 bariums that we've done before. And then since this is polyatomic, we want to keep it all together. We would go, whoops, not 3, 2, sorry. We would go PO4, we'd put it in parentheses, and then we'd say 2, because we know there has to be 2 of those. All right, so that's our formula for barium phosphate, Ba3PO4 2. The way we put the things together in the compounds is always the same. You find the charges of each ion and you make them balance. That's always the same procedure. The difference is just in how you find those formulas. If you have a polyatomic ion, you need to pull out its formula from a chart like this to do something like that. All right, so that's all about how to put ionic compounds together. A good way to practice this is just to pick random ones. You can also look online for some practice, and I'll have some stuff on Blackboard as well. Remember that I'm not asking you to name the compounds. I'm just asking you to put them together and draw the ionic compound, and that's it. So if there's any questions, I'll stick around for a couple minutes here, and then otherwise I will see you on Monday to talk about macronutrient structures. All right. Well, thanks everybody. Have a good weekend.